Hello. Uh, so today we're going to talk about 13.2. We're going to talk about limits and continuity. Okay. So first I want to talk about solving a limit. So I'm going to look at example 2. Example 2 is on page 886. Okay. So example 2, if we're finding a limit, this is just the limit as x, y approaches 1, 2 of 5x squared y over x squared plus y squared. Okay, so if you remember what it means for a limit to exist, if we can simply plug in the values into the expression and we get something that's defined, that usually is the limit. Okay, I'll plug in 1 for x, plug in 2 for y, so that's going to be 5 times 1 squared times 2, 10 on the top. On the bottom, 1 squared plus 2 squared. So that's going to be 5, and my limit should be 2, as long as my function is continuous at that point. Okay. Now, there's a lot of things to talk about. We can talk about continuity. We can talk about the idea of a limit. But this thing, a function is going to be continuous. Certain functions we know are continuous. The numerator is a polynomial function. Okay. Polynomial functions we know are continuous. The bottom, we've got a polynomial function plus another polynomial functions. Adding two continuous functions gives us something that's continuous. And then when we divide two continuous functions, we get something that's continuous as long as it's defined. So this looks like the only place this thing is not defined is when our denominator is 0. So it would be undefined and thus not continuous at the point 0, 0. Okay, that doesn't affect us because we're at this point. Okay, so this is our limit. Okay, now that we've solved a single limit, the first one, this is example number, what did I say, number 2? Okay, I'm going to talk a little bit about finding a limit. So last year in BC, when you found a limit, you had to check that the limit existed from the right side and from the left side. Those limits from the right and the left were the same. So if you had a limit, so this is just an example from last year, maybe you're finding the limit as x approaches 0 of 1 over x. Okay, so let's just look visually. We know what this graph looks like. It's going to be something like this, something like this. Okay, so as x approaches 0 from the right, we get of 1 over x. That goes to infinity. As x approaches 0 from the left, limit as x approaches 0 from the left of 1 over x, we get negative infinity, okay, because we're going to get a negative huge number, negative infinity. Okay, the limit from the left doesn't equal the limit from the right. Don't match. Therefore, limit does not exist. Okay, now this is where our biggest issue is when we try to find a limit of a function of 2 variables. Okay, because remember, a function of 2 variables, our limit, our function for this one, our function is f of xy is equal to 5x squared y over x squared plus y squared. So this limit, this function has a problem at the origin. Okay, but remember what this thing looks like. It's a 3-dimensional thing where our domain might be defined somewhere in this xy region. Okay, so let's come down here. Our domain on the xy plane, let's say our domain is some region like this. Okay, so that's our domain. At any point xy on this domain maps to some value z. Oftentimes we represent that as another dimension. So maybe it comes up here, and maybe that value is up here somewhere. Okay, so we might have this surface that kind of lies above this plane. So if we want to go to this point in the domain, the point 0, 0, we can't just come from the right and come from the left. We might be approaching from up here, from down here. You might be approaching along a line y equals x, y equals negative x. You could be approaching along a parabola. There's an infinite number of ways that you could approach this. You can't just approach from the right and the left, and as long as those two match, you know that limit exists. You would have to approach that point from an infinite number of paths, and that's not really possible, okay? So if we want to prove that a limit exists, other than something simpler like this, where we know it's continuous and we can just plug in the value and it actually works, okay? If that's the case, we can find the limit. But if it's not that simple, let's say it's not defined at that point, and we want to figure out what the limit is from an infinite number of paths going towards 0, 0. Okay, there's another technique that and we're not going to look at a lot of techniques to be able to prove this, but we're going to look at one technique to do that. We're going to look at that in a little bit. Okay, but first I want to look at a couple more cases, things you'll run into in your homework tonight when you're finding limits. Okay. What did I say? Oh, the other thing I wanted to say about that, one thing we can use this method for, if we want to approach from one direction and from another direction, and if our limits don't exist, as long as we find two pathways that give us a different limit, then we can say the limit doesn't exist. So for these functions, it's going to be a lot easier to prove that it doesn't exist than it is to prove that it actually does exist. Okay, I'm going to go to a couple examples from your homework. Okay, so if you look at number 30, you might get a limit that looks like this. Limit as x, y approaches 0, 0 of x minus y minus 1. Actually, we're not approaching 0, sorry. We're approaching 2, 1. X minus y minus 1 over square root of x minus y minus 1. Okay, so if we plug in 2 for x and 1 for y, that's going to be 2 minus 1 is 1 minus 1. We get 0 on the top. And they plug in a square root of 2 minus, sorry, you can't see that very well. Square root of 2 minus 1, so that's the square root of 1 minus 1. Okay, we get 0 over 0. Okay, so you might be thinking L'Hopital's rule. This is what we did a lot of times when it was single variable calc. But the problem is, if we use L'Hopital's rule, we want to take the derivative of the top and the derivative of the bottom. How do you take a derivative of something that has two different variables? Do we take the derivative with respect to x? Do we take the derivative with respect to y? That gets tricky. So we can't really use L'Hopital's rule. Okay, so what we're stuck doing is using one of these other techniques that you learned last year, and maybe we can find a way. We know that this value of the function doesn't exist here at the point 2, 1. Okay, but maybe what we can do is we can do something to this function to get it into another form. Okay, so the bottom is red x minus y minus 1. What if we multiplied top and bottom? Red x minus y plus 1. Red x minus y plus 1. So here's our clever form of 1. We multiply this. So the top, I'm going to leave that factored. So this is going to be the limit x, y approaches 2, 1 of, and on the top, I've got x minus y minus 1, and red x minus 1 plus 1. On the bottom, I get, okay, you're going to have to FOIL this out. So this times this gives you x minus y. Outers and inners cancel, and then you get minus 1. Now look at how nice that is. So this cancels with this, and it's just the limit as we approach this. Now we can plug in the 2 and the 1. 2 for x, actually there's no y, so 2 minus 1 is 1, square root of 1 is 1, plus 1, and we get the limit is equal to 2. And that works, okay? So let's look at number 31. Here's another example, okay? Let's say you have the limit as xy approaches 0, 0 of x plus y over x squared plus y. Okay, and if you plug in 0, 0, you're going to get 0 on the top, 0 on the bottom. We have the same problem. This function is not defined at the origin. Okay, so let's try a couple of paths. Let's say we're approaching this function along the x-axis. Okay, so we're approaching 0, 0. Let's say our domain looks something like this. We don't know what our domain is, but right now it just looks like domain is all real numbers. So it would be the entire xy plane. Let's approach along the x-axis. Well, along the x-axis, our y value is 0. So let's try along the x-axis. That means the y value is 0. So this limit, as x comma 0 approaches 0, 0, because remember, we're approaching along the y-axis, where along the x-axis where y is 0. So I'm just going to plug that in. And I'm going to put in the 0 for y. So on the top, I've got x. On the bottom, I've got x squared. Okay, this can reduce the limit x comma 0 goes to 0, 0 of 1 over x. And then we get something that's infinite. Okay. Now let's try along the y-axis. Which means x is 0. Okay, and notice this here, this could be either positive or negative infinity, because if you're approaching from the right side where your x is positive, you're going to get positive infinity. If you're approaching from the left side, you're going to get something that's negative infinity. So this limit does not exist. Okay, now let's try along the y-axis where x is 0. Okay, so we're going to try the limit as 0 comma y approaches 0 comma 0. And we're going to get y on the top and y on the bottom. Oh, that limit approaches 1. So right there, you know that your limits don't match. Okay, so your limits don't match, and so you can now say that your limit does not exist. Oops. Does not exist. As long as you find two paths that give you a different limit, you know that the limit doesn't exist. Okay. All right, let's go to example 4. Example 4 is another one. So the limit as xy approaches 0, 0 of the function x squared minus y squared over x squared plus y squared, quantity squared. Okay, plugging in 0, 0, you're going to get 0 over 0, you get undefined. So let's try some paths. I usually will try along the x-axis and y-axis first, which means the y value is 0. Okay, so that's the limit of x comma 0 goes to 0, 0 of, we're plugging in 0 for y, so we get x squared on the top, we get x squared on the bottom, let's square it, and we're going to get 1. Okay, so that's along the x-axis. Let's try along the y-axis. Limit as 0 on the y-axis, x is 0. So 0 comma y goes to 0 comma 0 of, and we're going to plug in a 0 for x, so we get negative y squared over y squared, quantity squared, so that's going to be negative 1 squared, we get 1. Okay, so we get the same thing. Let's try another path. Let's try it along the line. Usually in Excel, try y equals x, maybe y equals x squared, x equals y squared. Sometimes you try things like that based on this, and we're going to practice more of these. So I'm going to say along y equals x. So this is going to be the limit, as if y equals x, I'm going to call this x comma x, because that should be my y equals x. And I'm going to get on the top x squared minus x squared. Notice I've replaced the y with an x, over x squared minus, or plus x squared, quantity squared. And then you're going to get 0 over x squared. Oh, sorry, this is as that approaches 0, 0. Almost forgot what my limit was approaching, what my input was approaching. Okay, so what you get here is 0 over 2x squared, quantity squared, which is 0. Okay, so you know you're going to get 0 here. Now we got something that doesn't match. These both went to 1, but they don't match this one. So at this point, you can say that the limit does not exist. So a lot of times we're just looking for a pathway that gives us something different from the other pathways. Okay. And now I want to talk about, let's go to example number 3. Example number 3 is interesting. We kind of jumped around a little bit. And here's the limit as xy approaches 0, 0 of 5x squared y over x squared plus y squared. Okay, we're approaching 0, 0. We get 0 over 0. Let's start trying our different pathways. So along x-axis, which means y equals 0, you've got 0 over x squared. And 0 over x squared, which equals 0. I should have put a limit up here. Limit x approaches 0, 0. On a test, you just want to make sure you always fully document everything. Okay. So this would be 0 along the x-axis. Now let's try along the y-axis. So your x is 0. So that's going to be limit as 0 comma y approaches 0 comma 0 of 5. And let's plug in the 0 for the x. We get 0 over y squared, which is 0. Okay, I'm going to try another pathway. Say along y equals x. So this is the limit. X comma x approaches 0 comma 0 of, it's going to be 5x. If y is x, so that's going to be another x, 5x cubed over x squared plus another x squared, 2x squared. So you get 5. You can cancel these, cancel one of these. You get 5x over 2. Plugging in the 0, you're going to get 0. Okay, at this point, you might start to guess that the limit is actually going to 0. We might try another path. Sometimes if we can get, we might say y equals x squared. So if y equals x squared, we can plug that in. I'm not going to exhaust all the paths just because I know where this one's going. But if we have one method to prove, this book uses deltas and epsilons, and that's a method of learning calculus that you did not learn last year, so I'm not going to introduce that. That's just another way that you can prove some of these things. But we're going to prove this with the squeeze theorem or sandwich theorem. Okay, so our function is this. Our function is 5, this thing, 5x squared y over x squared plus y squared. Okay, and instead of proving that this limit, we think this limit is 0, can we agree that if we prove that the absolute value of 5x squared y over x squared plus y squared, if this limit equals 0, then our original limit would also equal 0. Of 5x squared y over x squared plus y squared equals 0. And yes, we can. If the absolute value is approaching 0, the absolute value of our function is approaching 0, then the function itself would also have to approach 0. Okay, because absolute values just make your quantity positive if it was negative, and when you're approaching 0, it doesn't really matter because you're still approaching something infinitely close to 0 from either side. So if this approaches 0, then this would also approach 0. Okay, so I'm going to take this thing. I'm going to prove that this limit goes to 0. And since we have this thing as an absolute value, we know that's greater than or equal to 0. We also know it's less than or equal to. Let's think about pulling something out of this function. Okay. let's just look at this thing in here. The x squared over x squared plus y squared. And you might be asking, why the heck am I doing that? Okay. I'm going to ask you, is x squared over x squared plus y squared always less than or equal to 1? Is that true? Okay. Think about this. If that y squared is 0, we have x squared over x squared, which is 1. Now, if y is anything else positive or negative, it's going to be positive when we square it, and it's going to make our denominator bigger, so it's going to make the quantity less than 1. Okay, do you want me to say it again? So x squared, a positive number, over x squared, a positive number, that's always equal to 1. If we add a positive to the denominator, it makes it less than 1. Okay, where is this going? Well, can I now say that this entire thing is less than or equal to 5y? Well, I can, because this thing is equal to this thing times this thing. So I just took this out. I took this out of this, and it was left with 5y. This times this always has to be less than or equal to 5y, because multiplying 5y by something less than or equal to 1 is only going to make it smaller. Okay? So if we have a 5y, we multiply it by this, then we get this thing, which has to be less than this, because we're multiplying by something less than or equal to 1. Okay, now let's put a limit in front of each of these. Limit as xy approaches 0, 0 of 0 is less than or equal to the limit 5x squared y over x squared plus y squared. This is as xy approaches 0, 0 is less than or equal to the limit as xy approaches 0, 0 of 5y. Well, this limit equals 0. This limit, plug in the 0 for y, equals 0. So that means this limit of 5x squared y over x squared plus y squared, whether it's this or the absolute value, has to be squeezed in between 0 and 0, and therefore the limit of 5x squared y over x squared plus y squared is equal to 0 by the squeeze theorem. And I will tell you this much, this is the only theorem we're going to have to prove something like this in this chapter. Okay? One last concept I want to talk about is the concept of continuity. If you look at example number 5, number 5 is on page 889. So example 5, it just says to discuss the continuity. And we discussed this a little bit. So if you understand continuity, you can stop now and get started on the problems. But discuss the continuity of these two functions. A, f of xy equals x minus 2y over x squared plus y squared. So this is like the one that when I talked about continuity in one of our earlier examples, I think example number 2. Okay, this function, the x, y equals x, or some function equals f of xy equals x is continuous. That's a polynomial function. This is continuous, another polynomial function. Compositions of polynomial functions are also continuous. Okay, and then this is a polynomial function. So on the bottom you have a polynomial function. Dividing polynomial functions will also be, dividing continuous functions will also be continuous anywhere where those functions are defined. Okay, so the only place we have to check is where this thing is not defined. So it's not defined, therefore not continuous. When it's not defined. The only place it's not defined is at the origin. Not defined at, not continuous at 0, 0. Continuous everywhere else. Okay, let's look at B. Okay, and this is f of xy is equal to 2 over y minus x squared. Okay. Again, your numerator is a continuous function. Your denominator is a continuous function. Compositions, quotients of continuous functions will be continuous as everywhere that they're defined. This is only not defined when y minus x squared equals 0. So I will just say it's continuous everywhere except on y equals x squared. Okay, except when y equals x squared. Okay, that's about all I'm going to talk about today. Go ahead and get started on those problems.